So I'm going to go ahead and do a video. I'm going to be showing some problems on this worksheet on continuity and the IVT. Okay, so I'll be doing a few problems in this video to help you get started on your homework. Problem number 1 through 4. Sketch the graph of a function f that satisfies the stated conditions. So from number 1 through 4, we're going to be drawing some graphs that that pass these certain conditions. So we'll probably be doing 4 different graphs, and then we're going to go ahead and just double check to see if they do satisfy the conditions that are provided here. So number 1 says f has a limit at x equals 3, but it is not continuous at x equals 3. So let's go ahead and do a brief review of what it means for a function to be continuous at a point. So if you remember a few videos back, or a few lessons back in your class, a function is continuous at x equals c if and only if, number 1, f of c is defined, number 2, the limit at x approaches c of f of x exists, and number 3, that the limit and the function value are the same. So number 1, let's go ahead and draw an x and y value. I'm sorry, x and y axis, and then let me just read it again. The limit exists at 3, but the function is not continuous. So if I were to choose a condition that would satisfy number 1, it would just be number 2, condition number 2. So the limit exists, but the function value does not exist. So at x equals 3, so I can just say 1, 2, 3. I can draw a hole anywhere I want to, like that. It doesn't matter. I can draw a graph like this. Sorry. So it's got to be touching the dot but not crossing through it, and then there it is. So I see that my limit exists because as I approach 3 from the left, 3 from the right, I also approach some y value. Well, some value, I don't know, but the limit exists. But f of 3 does not exist since it's an open hole. Number 2, we have f is continuous at x equals 3, but if its value at x equals 3 is changed from f of 3 is equal to 1 to f of 3 is equal to 0, f becomes continuous. So here we have an example where, to begin with, the function was not continuous at x equals 3, but if its value was changed, it would become continuous. So pretty much we would have condition number 2, and then we would have to change the way the function looks like so that we get condition number 1, and then in order for it to be continuous, condition 1 and 2 must equal, which will yield condition number 3 to be satisfied. So example number 2. So it said here that f is not continuous at 3, but if its value was from 3, 1, now it's to 3, 0, it would be continuous. Okay, so let me go ahead and draw all of this in here. So let's say we have a 1, 2, 3. 3, 1 would be like right here, and I'm going to go ahead and draw its close dot, and I'm going to draw my graph like this, like that. Okay, so example number 2 is saying that if I were to change this point to this point, clearly it would be a continuous function. And then you can go ahead and scratch this point off, saying that it's been removed and or changed, and that would satisfy number 2. Number 3, f has a removable discontinuity at x equals c. C is an arbitrary value for which f of c is undefined. So at x equals c, we have a hole since it's a removable discontinuity. So here goes example number 3. You can choose whichever value or whichever side of the y-axis to be your c. I always like to choose the positive side, makes it more easier for me to read. So and there it is. F has a removable discontinuity at x equals c for which f of c is undefined, and here is c, and if there was an f of c, it would be right there, but there isn't. Example number 4. So that was number 4. That was number 3. We can do number 4. F has a removable discontinuity at x equals c, for which f of c is defined. So we have the same example as number 3, except now it's a removable discontinuity where it is defined at c. So I'm going to draw it exactly the same. Here is c, except that now f of c is defined, but it's not exactly at where the limit's at because it's still a discontinuity. So you can choose either up or down. It doesn't matter. However you want to draw this, one of these two examples will satisfy number 4. Now I'm going to go ahead and do one of the problems from 5 through 7 so that you can gain a good understanding of how to do the next two problems. So I'm going to go ahead and do number 5. From problems 5 through 7, use the definition of continuity to prove that the function is discontinuous at the given a value. Sketch the graph of the function. So here goes number 5. I'm going to go ahead and snip this thing out so that I can work on it. Or I could just move all of this. Okay, so we want to prove discontinuous at x equals 1. Okay, so we're going to go ahead and follow the 3 conditions of continuity. So let's go ahead and just plug in 1. So f of 1, if I were to plug in 1 right now, I get 1 squared minus 5 times 1 plus 4 all over 1 minus 1, which is a 0 over 0. And if you remember from class, 0 over 0 implies removable discontinuity. Removable discontinuity. Okay? Now, if there were to be a dot filled in at x equals 1, you would take the limit. So this is extra. This is not part of the problem. But if I wanted to fill in the dot, if it were to exist, the limit would tell me how, or what value would that be. So I would take the limit as x approaches 1 of x squared plus 5x plus 4 all over x minus 1. And I notice that I have a quadratic on top. And it seems factorable, so I'm going to go ahead and say that x minus 1 and x minus 4. A big hint is that anytime that you know that a quadratic is factorable, the bottom factor will always be a top factor as well. So a lot of times in the AP exam, they'll give you something like that. You just got to understand they're not going to give you anything you cannot compute algebraically if it's non-calculated. We see that those factors cancel, and now I'm left with the limit as x approaches 1 of x minus 4. And if I take the limit right now, it would be a negative 3. So the graph, this graph right here, is actually linear. It's linear because this is my final equation after I factor it. So it would be 1, 2, 3, 4. There's my y-intercept, and at x equals 1, and at 3 there would be an open hole like that. So that's what it means for a function to have a removable discontinuity. So even though this is a rational function, it's actually linear because of the factors that cancel, but with a hole because of the 0, 0. Okay, let me go ahead and do one from below. Number 8, we have use the definition of continuity to find the values of k. and or m that will make the function continuous everywhere. So I'm actually going to go ahead and continue this since I'm running out of time in my video. I got 10 minutes. I'm going to continue number 8 and do some more problems on this worksheet in another video. So I'll see you in the next one.